Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you're watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right. Hello, everybody.
You know what's really disappointing about this?
What's that?
Wait, that right here. There should be a meme right here.
That's right.
See how my finger disappears? I can't.
I know.
I can't. We're in different places.
Hold on.
Problem.
There is. Well, not exactly. Let's see how close can I get with the meme?
You'll have to like duck. Yeah, if you like just duck for a minute, I bet you could see it. It's like, there you go.
That's it.
Yeah, just do the whole live stream. Like
do the live stream like this.
Like you're reclining. All right, and the next question.
All right, what's the next question? Oh God! All right. Okay. Sorry, Winnie. Hopefully, people got a chance to see it. Otherwise, you'll have to go back.
I feel very. It's like you feel naked. You know what I mean? It's like you were missing something critical to the live stream. Some really amazing meme that gets me on a soapbox about things like impedance potentials and Lugan capillaries or whatever the case may be. I don't think I made one about Lugan capillaries yet.
Oh yeah. You could make you can make one about Lugan capillaries.
I know this is not the time to brainstorm, but I'm going to do it anyway. So I want to make one that has school children walking through a Lugan capillary because you'll find it funny and no one else, and I think that's enough. Because you and I will find it funny, and I think that I have to do that at some point. That's
absolutely.
A bunch of school children walking through a Lugan capillary. Okay. Well, all right. Welcome everybody.
Yes, welcome everybody. And it looks like we do have some questions coming in. Thank you for joining us. Let's get started. It looks like Apoorva Porvapod-R50 is asking, hello, thank you for the wonderful live sessions. I have a few inquiries. One, how do we calculate the ring area in RRDE? And then why the currents are not usually normalized with area in ORR? If normalized with area, the disk current should be normalized with disk area, and ring should be with ring area. Correct. So this is a good question. I think we've had some questions like this before in terms of the nature of why don't we take the current, like the current density into account versus just the current often is the case.
Yeah. Well, the first part of the question is actually, I don't want to say simple, but just for lack of a more careful wording, I suppose. How is it calculated? Let me know if the sharing is working here. Am I sharing? Okay.
You are sharing.
Okay. So just not to be silly, but to be real for a second, and just in case this isn't clear, and perhaps apologies, Apoorva, if I'm misinterpreting your question, but how if you're you're literally asking how is the ring area calculated? I mean, Frank, there's nothing special. If you're asking like electrochemically active surface area, that might be a different situation. But I mean, it's just geometry, right? I just wanted to make a very simple point that in case this wasn't clear. But if this is like R1 and this is R2, like radius 1, radius 2, right? It's just pi r squared, R2 squared. That's the area of the circle R2 minus the inner circle. That's a terrible. You can't read that. So sorry. Pi.
No, there is an equation thing.
There sure
There,
is. But I'm
there are
I'm
two
knee
things.
deep. I'm knee deep in trying to write this. So I'm just gonna
There's a
keep up.
shape tool in PowerPoint and
Look,
an equation
okay.
tool in
I've
PowerPoint.
had it with your logic, mister. You know?
Sorry, continue.
Yeah, I'm gonna carry my amazing chicken scratch writing through
But
here.
it works. This
It
works.
does.
Yeah,
It does. Yeah.
this
So
does
anyway,
work.
the point I was making is this is somewhat of a simple point, and maybe you kind of already figured this out, but I just wanted to be clear. How is the ring area calculated? I mean, literally, it's just simple geometry. It's just basically pi r squared minus pi r squared. You can put it into r2 squared minus r1 squared. So that's just how the area is physically calculated. Just to be clear,
Yeah.
I know that seems kind of rudimentary, but just you did ask the question, how to calculate the ring area.
Yeah.
That's how.
And she does have a follow-up sort of say because we have a question in between, which is in many papers only disk area is mentioned, not the ring area, and geometric area will be written, and they infer to the disk area, but not much on the ring. So she's confused, or Porva is confused.
Yeah.
But yeah, just to kind of add a comment to it, the ring is just thought of as like a detection mechanism, and the collection efficiency, the geometric, the collection efficiency of a ring disk electrode is based entirely on the geometry. I think we have a whole article that goes over its calculation from kind of Albery's papers,
Yeah, let me
over
check
50 years ago.
I think we have that. I'll check. Try to find
And and so once the disk, and people are usually interested in the disk area mostly because that's where their catalyst is drop casted on. So the detection, of course, is on the ring. Most people aren't putting stuff on the ring, so the ring area isn't needed. What's mostly important is, you have a disk area that's so big, and you're putting so much catalyst on it. So that becomes a better way of quantifying how the catalyst is put on, and the catalyst activity. And then once you know the collection efficiency, then as a percentage, then everything else kind of just takes care of itself. So the ring area isn't needed quite as much. So hopefully that
and just to be clear to your point, Alex, the RRDE paper that you referenced, I just made a link to it in the chat. So
nice.
Section 5.1 is where it starts talking about the theoretical computation of the collection efficiency, and then an empirical measurement of the collection efficiency. And I think just further to your point, Alex, about why we wouldn't normalize it, is that because it's a detection, it's an absolute current measurement. We are detecting the presence of something that was made at the disk. The amount of something that is made at the disk is related directly to the current. The current is a rate of flow of electrons. And then through like Faraday's law of electrolysis, we figured that's how many moles of the thing was made, how many molecules of my stuff was made. And then I detect it at the ring. So I'm comparing, like with a detection of a ring in a ring disk experiment, I'm basically comparing the raw current of the disk in the ring to see how much of my thing did I detect, and then I can normalize it based on the efficiency value. Only with reporting the value, like in a paper, would you report like the disk current, because that's how you're going to relate to other papers in the literature, because you're looking for like milliamps per centimeter squared on the disk current, because that's the reaction of interest, so to speak, right? The ring is just more there to say, like, okay, well, here's my performance of my material on the disk. Here's all of the metrics and all the things that I want. Also, we verified using the detection on the ring the presence of XYZ, whatever it is, and here's the percentage of how much I made. But the ring isn't really as necessary to be reporting like what its raw current. I mean, you would provide that usually in, like, let's say a supplemental information if you're publishing, because it's like nobody really needs to see like exactly how many milliamps per se you got on the ring. Like, you just want to say I got like an efficiency of 82% for this reaction because I detected the product at the ring, whatever the case may be. Maybe that provides a little more context. I hope it might still be a little confusing. I know RRDE is pretty complex.
Yeah.
In
She has one, Apoorva has one last comment, at least, that just came in, which is, and while calculating the Faraday efficiency, we should use absolute currents, right? I think so. I think
so.
I think you would use absolute current, and Faraday efficiency. I feel like it has numerous. I think it needs to be clarified how it's calculated, but usually the efficiency is also related to how much of the product, right? If you're doing catalysis, did you generate? And you usually would even use other techniques like mass spec to say like, oh, I got so many moles of my product, and I put so many coulombs of charge, and then considering the number of electrons transferred, how many, divide by the number of electrons transferred, how much, did I actually get an equivalent number of moles of product out, compared to the charge that I put in.
Right. And working the other way, it's like I got this many moles of my product. That should have correlated with this many like coulombs or amps or whatever the case may be. And this is how many amps I actually got or whatever, or how many coulombs I got, probably integrated charge right over time. And so then it is absolute in that case because it's the raw number of stuff that was made, and that is based on absolute current. That's correct.
Yeah, that's good. I think we covered all of Apoorva's questions.
I think so. Yeah, follow up Apoorva if there's something you still need. Or
we didn't.
Some clarification on, but I think we kind of covered you there.
Yeah. Sometimes we jump around based on what's important or somewhat. But all right, moving on to the next question. Hi, regarding the EIS, how is excitation input signal looks like characteristics? I know it is a sweep sine signal, but the question is, how is it applied? Is it like one signal with a specific frequency, then measure the output current and do FFT, fast Fourier transform, then move to the next frequency, or it sweep all frequencies at once, then measure the output and get the FFT?
It's almost like I did a webinar on this. I can show the first few
Yeah,
slides.
right.
I can show the first. I can just do a little bit from the beginning of my impedance theory webinar if you want to kind of talk through this. I pulled up the wrong one. Hang on, that was the wrong one.
Oh yeah, no, and so one kind of quick answer to the question is that I believe we do the FFT at each frequency, kind of in real time, and you can even prove this to yourself because when you're doing an EIS experiment and you watch the Nyquist plot being generated, if we waited for all the frequencies to go through before doing an FFT, we wouldn't be able to do that. Like the Nyquist plot would just show up. But because you can see each point on the Bode plot, you can tell like, oh, we had to do a Fourier transform of those sine waves to get the data to create that one data point. So from an order perspective, it is, you take one frequency, frequency input, frequency output, fast Fourier transform, get the magnitude, some crazy magic to get the phase angle, and then
that's exactly
and then you plot the data point.
Yes, it is definitely magic. So exactly to what you just said, Alex. Ahmed, I'll kind of step through this for a few minutes for you. Hopefully this kind of helps a little bit. So this is from my webinar, my impedance webinar on impedance basics. So check out our YouTube channel in our webinars playlist. I've given this webinar, I think 3 or 4 times. And this is from the first one of 5, basically. So an impedance experiment consists of the input sine. So you're asking what the input sine wave looks like. I mean, it looks like this. So this is just whatever your system is electrochemically, and then this would be going through the cell cable. But it's a sine wave centered about some baseline. So the mathematics of a sine wave are E of t, which is a time-dependent signal. That's what this green line is. And then we have E0 or E naught. That is the sine wave amplitude. We have a frequency, which is this omega, and then time. And frequency is usually in units of hertz, but technically for mathematical purposes, it's radians. But the dotted line here in the middle, that's the baseline. So what does it look like? Well, it's a sine wave, so it goes up and then down periodically about some middle, and you pick that middle, you pick that baseline, and then the E naught or the E0, this is the peak. So that's how high up it goes or how far down it goes around the baseline. So again, I'm just trying to be very specific to your question, which is that what does it look like? That these are the variables for what it looks like, and this is where they are mathematically. Sometimes you'll see RMS, which is called root mean squared, or peak to peak. These are just different ways of categorizing the amplitude of the sine wave. You'll see in software, but it's all related to the same sine wave. They're just different ways of representing it. And then 1 over the frequency is the period. So for example, a 10 hertz sine wave takes 1/10 of a second to complete. Right. So 1 megahertz, you get 1 million sine waves in 1 second. The faster the frequency, the quicker it's over, basically. So input output, right? I think part of your question was what's the output, or what are we measuring? Well, of course, if the input is potential, the output is current. You can do it the other way. If the input is current, the output is potential. The output signal will have the same frequency as the input signal, and it may or may not be shifted. And so there's this phase angle. So you can see, for instance, that the peaks might line up, they might not line up. As Alex said, there's some sinister black magic that is used to figure this value out in the software. When analyzing the signals, it's apparently very complicated. It looks like it should be very easy. Just take the difference in here and get an angle, but it's apparently really crazy and complicated. That's above my pay grade, apparently. So, but in any case, you can visualize basically that the peaks might be shifted, and the current will have its own sine wave, same frequency, but perhaps its own amplitude, and its own phase shift. Okay. And then again, to your point, you said, well, how is this done? The impedance experiment typically consists of doing a range of frequencies. We typically start fast, and then we go slower, we go slower, we go slower, and then we're done. So that's the order of an impedance experiment. And the last thing I'll add to your question, which was, can we do all of them at once? There is a kind of impedance experiment where you sort of do, maybe not all, but more frequencies at once, and that's called a multi-sign experiment. And so that's when you overlay a bunch of those frequencies into a single signal. It's a bit complex, and it might be tricky to draw, but I'll give it a shot. But you can imagine if my input signal, I'll use green again because that's what I use in my slides, is some frequency. I have a nice looking sine wave, but if this is frequency 1, and then I have, let's say, frequency 2, and it's a faster frequency, right? So it's whatever. There's more per time, right? Well, I could combine these two. You could think about making a combined, if I add these two together, gosh, this is going to be terrible, but I'll try. You can imagine it might look something like this, where it's like, it's got this periodic, waveform to it, but it's also got like another signal kind of. So it's like it's the addition of two sine waves. So it looks messy. The point of this is that when you do something like FFT, which is fast Fourier transform, or DFT, which is called discrete Fourier transform, these are methods that can deconvolute signals, sine wave signals. And depending on the choices that you make for which frequencies to include together, DFT or FFT can actually deconvolute multiple sine waves at once. So this is what a multi-sign experiment can do. There's a larger discussion that we can have about pros and cons of doing a multi-sign, and it's not quite so cut and dry. But just to be clear, there is a possibility, let's just say, of doing maybe not all, but some more than one frequency at once in a multi-sign EIS experiment. although it is a little bit less common.
Nice. Nice. And kind of while we're somewhat on the topic, we can extend this out. The next question is, please explain Bode and Nyquist plots.
Well, I should just kept my presentation up, I guess.
Yeah, you can just, if you want to just keep your presentation up.
Let's get to the math part of it, I guess, and I'll just keep going there. Hang on, let me get that up. Yeah, how are Bode and Nyquist plots? Also, you should link your short because Alex.
Yeah,
just made,
like I literally just
this way. Alex just made a short about the relationship between Bode and Nyquist plots, and it's really good.
It's all of 50 seconds, so
yeah, 50 whole seconds long. So
50 whole seconds.
if you have 50 free seconds in your day, if you can find a way to grab 50 seconds, watch the short on our YouTube channel. It's quite informative for that. So, but I'll try to explain briefly how Bode and Nyquist plots, what they are, or how they come. So I'll start with this slide, just getting into it, which is that the mathematical expression of impedance when you're doing it is here. I'm skipping some steps on the previous slide intentionally here, just trying to move on a little quickly. But basically the impedance can be broken down into impedance magnitude and phase angle. And then there's the imaginary number. So basically the mathematics lead you to complex numbers, to the complex plane, if you will. So this J is the square root of -1. Basically, it's just math. Like, people get tripped up by the imaginary impedance. It's just mathematics. That's it. It doesn't mean that the impedance isn't there. It's just math. So basically what we have is that the expression, once you've done an impedance experiment, that you get is this one. You can break it into the real and the imaginary components, as we do with any complex number, if you recall your mathematics from maybe high school or undergraduate. So the real part of this expression is z magnitude cosine of phi or phi, and then the imaginary part is z magnitude times the sine of the phase angle. So this is where the zr and the zi come from, and so this is just the a plus bi, real plus imaginary parts. It's just where this comes from. And so in total, when you've run an impedance experiment, you had a whole bunch of frequencies, like I just showed previously, usually fast, medium, and then slow, or whatever the ones you've chosen are. So you have a list of frequencies that you did. When you measure the signal, the input and the output, you get a z magnitude, you get a phase angle, as I showed in the diagram of the sine waves. And then you get the zr and the zi. That's what's calculated up here from those quantities. And so where do the Bode and Nyquist plots come in? Well, they're just different plots from these 5 columns of data that I just mentioned, right? So the first one's the Nyquist plot is taken from z real and z imaginary, usually minus z imaginary. But these two calculated quantities from the math of that complex equation is what makes a Nyquist plot. And so that's where you get stuff like this, where you get it's another way to call it is like polar coordinates. But these semicircles and everything like that is what you get from the z real and the z imaginary variables of your impedance data. And then the other 3 variables, frequency, impedance magnitude, and the phase angle, these are the ones that are sort of directly measured from the sine wave signals more directly. That's the Bode plot. That's where that comes from. And you typically plot it log scale. And this shows you the behavior of the impedance overall, as well as the phase angle as a function of frequency. So those are the Bode and Nyquist plots. That's where they come from the data that you get from an impedance experiment.
Nice. So we have I think this is actually a follow-up question from the last live stream that we had. 7476 is just saying getting oxidation peak of azithromycin at 100 micromolar concentration, but when you move to 1 to 50 micromolar concentration, it's not getting any peak. Change the amplitude as well for like a differential pulse voltammetry experiment, but not getting any peak at lower concentrations. Any suggestions? So this was the running into a limit of detection type of issue with observing a peak. And I believe differential pulse was the technique we were talking about last time. Maybe you were using square wave as well.
Well, this one doesn't say which method he's using, right? I don't think it says.
Correct.
Okay.
Yeah, he has not mentioned the method. I'm just
I assume
remembering like
CV.
last time.
I assume
he's using
CV.
CV?
Well, that's this question. The person
Yes.
asking this question last time you suggested DPV, so I think the
Oh,
suggestion
yeah.
is the same. Is my point. I don't think this person is necessarily using DPV unless they
Mhm.
could clarify if I'm mistaken.
Yeah. You can clarify the technique that you're using. You just said that you changed the amplitude, which is one of the parameters. Just a
Oh,
DPV
amplitude.
parameter. That was the
Yeah.
only
I think
thing.
I think you're right. Yeah, no, amplitude implies peak.
But we'll see. We'll see. If you want to leave us a comment to let us know if that was the technique that you're using. One suggestion, one thing to at least think about is if you have your electrochemical system set up, you have 100 micromolar, and then and you're getting signal. Everything seems to be working. If you're preparing separate solutions and preparing separate, electrodes and things like that, I would just take your 100 micromolar and then dilute it, and I would just keep diluting it. If you're starting with 100 micromolar and you're just preparing separate solutions and then you're re-cleaning or rechecking all of your electrodes and stuff, I would continue to I would keep the same system where everything's working, and then I would do like a serial dilution, if you will. So if you had, say, let's just make numbers easy, if you had 50 milliliters of your 100 micromolar solution, if I diluted it by adding, I might even just keep adding volume to it, even 10 milliliters at a time, do another DPV or another CV, whichever technique you're using, and then just see at what point, because 1 to 50 micromolar seems very specific. You may find that it's like, 65 micromolar, and then nothing happens. But this way you can actually see exactly all the same parameters. Nothing changes for your electrode. None of those things change. Just see how low you can go in concentration to know that, it's not at 50 micromolar, it's actually at some other value. But this allows you to make sure that every other experimental parameter, electrode preparation, reference electrode working, all those things, those are not playing a role. It's just and you keep on adding the electrolyte. You still need to make sure that you have the same electrolyte of your azithromycin, just it doesn't include the azithromycin. So I would do that. I would do a serial titration, if you will, to figure out the limit of detection. Because then you might start to play around with other parameters and to remove the possibility that some other fundamental phenomenon is not happening. So that's kind of my initial, based on what you've described, that's my initial suggestion or take on your situation, not knowing anything else. Any other?
I have no comments. No, I think you're right. Yeah, finding that limit of detection more systematically, the way you just described, I think is the right approach. Because ultimately, I think that's the case. Like at some point, the fact that you're not getting a peak isn't your fault. Like that's just this is just science at some point. Like it's not physically possible for that particular catalyst with its activity, its surface area, whatever the case may be, to really measure, your reagent. So, you could change all the different variables to try to improve your limit of detection. Otherwise, if that's the system that you're using, then quantify as best you can what the limit of detection actually is based on what Alex just said. And I think that's the right approach.
Yeah,
for sure.
All right. So give us any comments if you still have further clarification, but if not, we'll move on to the next question. Just going in order, Apoorva's asking, in EIS Nyquist plot, is is that okay to get negative Z imaginary to be started from negative? I mean, the measurement will start from the negative y-axis in the Nyquist plot, which in a way is positive imaginary impedance.
Yes, of
And
course it's
yeah,
okay. It's more than okay. No, it's just
it's just okay.
yeah, it's just it's a little okay. No, when you have it's starting in the negative region, that just means you have leading inductance. So something like this. This is a very basic example. So just here's a semicircle, and it's down negative. So you can see this is the y-axis here. Here's 0, right? So I have like a semicircle, but oops, there's a negative tail. That's just a leading inductor. So you can see that the circuit is right here. It's like it's not Randall's. There's no Warburg element, but I sometimes just say Randall's for shorthand. But an RC, RQ, whatever you want to call it, that makes a semicircle, and then there's a leading inductor. And so if I didn't have an inductor, if it was basically 0, you'd see I just have this semicircle. But as the inductance value grows, it starts to show up at high frequencies, which which I assume is what you're calling the start or the beginning of the Nyquist plot, which is the left side of it, basically. And that's where the tail, if you will, starts going down. It's just a situation where there's inductance. That's all. Cell cable inductance. So no, it's not a problem. It's somewhat common with particularly like batteries. Often illustrate inductive effects at high frequency often show up as a result of the cell cable itself, and they often show up in systems that have a very low impedance, which batteries tend to do. And they show up, and you can honestly, a lot of times you can fit an inductor as a leading, in addition to the leading like resistor or uncompensated resistance, whatever you want to call it. The inductor is not like, I should say, relevant or even interesting in a lot of cases. It's just like related to the cell cable or the physical setup of your instrumentation. It's not often, although there's some exceptions, but it's not often attributed to properties of your actual system, like your battery and everything else. So it's often like you can fit it, or you can just sort of skip to where the y-axis is 0 and then positive, or in the it's really negative, but basically where the data is where you want it to be, so to speak. You can often just sort of skip those data, and it doesn't usually mean there's anything wrong.
All right, very good. Moving on, just a comment. It says, hello, I'm an electrochemist from Italy. Me and a research group love the content of the ducts. Greetings, Alessandra and Simone. Keep up the good work. Thank you. Appreciate it. All right. So the Vetyob is saying, hi, thank you for your valuable time. Could you please briefly talk about two-electrode CV and peak analysis?
First of all, you don't know my time is valuable. You shouldn't.
Yeah. Yeah. So you have a two-electrode. Yeah. So you have a two-electrode setup. Actually, let's draw some of this stuff. I haven't had a chance to draw anything.
Yeah, you should draw. I've been drawing too much, and I'm clearly not good at it. So you're good.
No, you're great at drawing, and I think I should be sharing. So.
Yeah, you're good. You're good. Well, you're drawing anyway. I'm not sure if you're good either, but we'll see.
Yeah, no, that's true. So this is a case where you have these two electrodes in solution, right? And you don't have, maybe you have a voltmeter in between, or you have a potentiostat in a two-electrode configuration. And we'll just call this one, electrode 1, and this one's just electrode 2. Working encounter. So generally speaking, the problem with doing CV in a two-electrode configuration, there's a couple things that happens. Normally, so let's say you get a CV. Maybe it'll look like this. Maybe it won't. But this is your typical duck-shaped voltammogram. Say you have an oxidation reaction, and then you have a reduction reaction. So the issue often is the fact that the potential here will shift, right? And one of the issues, of course, that you've asked is, because I've seen you ask this other thing, which is how can it be confidently interpreted? And the confidence I think the truth is, when you have CVs that look kind of like this, you cannot have confidence in the values, because you are missing a reference electrode. You are missing a third electrode, 3, which is your reference, the thing that has a stable potential. Now, there are, of course, certain situations where this is actually okay. It's okay to have a 2-electrode electrode configuration. But that instance has to do with the following. And that's mostly when you have what are called microelectrodes. So typically you need to use microelectrodes for confidence in CV. Confidence in CV for 2-electrode configurations. And so the reason why we end up having stuff like that, why is this the case? Like, okay, well, why do you need microelectrodes? And the reason why is because of the current. When you have a lot of current passing, the potential of working 2 will shift. So this shifts with high current. This is when current is up. When current is really big. And you can even think of it just kind of fundamentally, almost as if it was a resistor, or just what is required. The potential of these electrodes, right? The potential of any of these electrodes is based on the surface charge. And if you have a big area electrode where there's lots of current, then you fundamentally have to move the potential quite a bit to make this thing shift. So that creates inaccuracy in your voltage. But if you have very small electrodes, when you have really tiny, microelectrodes, and sometimes a microelectrode will be like something encased in glass, the very, very tiny area. And let's say you have a big, kind of, say it was a graphite rod or something, and that was your working 2. Well, the amount of current that passes is really tiny, but it does give you good CVs. You can get these kind of steady state voltammograms with microelectrodes. But of course, maybe you have bigger electrodes, so you can't actually do that. But generally speaking, the amount of current, if it's nanoamps of current, oh man, like that barely actually creates shifts in the potential of your other electrode. It barely creates any kind of change in, quote, working 2. So there's actually a bunch of people who don't even use potentiostats when doing micro or even nano electrochemistry, because to actually change the potential, this doesn't actually need to change the potential very much to generate the amount of charge needed to make big changes in the potential of this microelectrode. So that is, and that's kind of an interesting thing in general that I'll mention and kind of conclude with, which is that the potential of your counter electrode in a 2-electrode configuration, or even in a 3-electrode configuration, can vary wildly, just to make sure that the potential of the working electrode is fine, is whatever you tell it to in the potentiostat. So the counter electrode can actually change quite a bit, but we take steps. We either don't care about it, or we take steps to minimize how much that potential changes. So So event Yab, I don't know if you added any extra
No, I just
comments.
wanted to
Doesn't
note
look
that
like it.
Aporva just asked the same question, so we're covering two
Oh,
problems.
okay.
So is it okay
Yes.
to perform CV in two-electrode system? Yes.
Yes. So the answer is yes. There are things to keep in mind, but if you are working in a large area, if you have a large area electrode with lots of current, the accuracy of the potential and the x-axis will often be wrong or incorrect. But maybe you don't need that. Maybe that doesn't matter for what you're looking at. So hopefully that was helpful. Let us know if you have further clarification or need further clarification.
Yeah, we can talk more about two-electrode
talk more
systems
about
if you need us to.
Yes.
But yeah, for now, I think we can move on to this.
Yep.
It's actually not a question, but I don't know if it's just sort of wanting to know why. But Hard Rock University, which is that a real university? Interesting. Says, I have a situation where I am electrowinning out of a sulfuric acid solution. I put carbon anodes in the new cell instead of the old sacrificial steel ones. It seems my cell resistance went up. It seems like more voltage needed to get the same amperage. Yeah, that does seem to track. I guess my question is, do you have a question, or are you just trying to understand what's happening?
Oh yeah.
Is
Yeah.
that
There's no question mark. It's just a statement.
yeah? I mean, it almost seems like you're just. I mean, perhaps what you're discovering is that for instance, the only thing I can think just right off the bat, for example, maybe this doesn't perfectly explain it, but we use graphite or carbon, whatever the specific carbon is, pretty frequently, obviously in electrochemistry, and sometimes as a counter electrode as well. But carbon itself is kind of hydrophobic, um, oddly enough, even though it works quite well as an electrode material. Carbon is just a little bit hydrophobic. So I don't know. I mean, it's possible that that adding, substituting, steel for carbon is increasing the resistance a little bit because it just doesn't like wet as well or something like that, or that the carbon isn't maybe. I guess I don't 100% know what's going on with your system. Maybe it's a two-electrode system, because if it was three-electrode, I would assume that the sacrificial side, the anode side, that is, I would assume, like the counter electrode in this case, if you have a reference electrode present, the resistance of the counter electrode shouldn't really play a role. But you say cell resistance, so I'm assuming it's like a two-electrode system. So back to the point you kind of just were talking about, Alex, it's like if it's a two-electrode system, then it is involved, entirely in your measurements or whatever. And then, I don't know, like if you're using a sacrificial anode, the downside is that it goes away over some period of time. The upside might be, from what you're discovering here, is that because it's a sacrificial electrochemical reaction, it's actually pretty like favorable, like thermodynamically, and so it might have a relatively low resistance associated with it, because it's like, you might be inclined to use something like carbon or platinum or something because it won't go away, it won't get destroyed over time, it gives you the current that you need. But the sacrificial steel, if it's just corroding away as you do your process or whatever, excuse me, the case may be, it might just be like super, like easy, like it kinetics work great, and the resistance is low because it's like very easy to destroy this thing, the steel, as the other side of your cell, so to speak. So it's like, I'm just trying to point out, like, there's positives and negatives. Like, it might stink to have to replace it periodically, because if it's degrading, well, you have to probably eventually substitute a new sacrificial anode in, right? But the trade-off is that it has lower resistance, and so it's just going to be a little more preferable. So I don't know. Again, if just check if there's there's a little bit of follow-up here. not a university.
Yeah, no, just trying to understand these using 304 stainless steel.
Old carbon steel anodes to 304 stainless. Trying to understand. Ran out of text. Yeah, okay, right. I got it. Yeah, no, of course you're working on the confines.
Yeah, just typing on the.
Yeah, I get it. Yeah. New
Yeah,
carbon anode is new is carbon anode to 304 stainless.
Plating gold from
Wait, carbon stainless steel is not carbon. Stainless steel is mostly iron. I guess I'm just trying to understand here, but perhaps the natural cell voltage is competing with the applied voltage at the electroplating system. Plating gold from acid solution. Yeah. I mean,
another
I think
thing to think about is that the current. I think this kind of hits on what you were saying earlier, Neil, which is that the current in your system is like the constant, right?
Yeah.
Like the current that happens, like because you have a sacrificial carbon anode or steel, you're plating onto something else. The total current of the system between those two things must be equal. Like the plating of the gold onto whatever your cathode is, and whatever reaction and oxidation that's happening on your anode, those two currents have to be equal to each other. And so if it's harder to have an electron transfer at your carbon rather than stainless steel, then your total current is, the resistance is going to be higher. You need a higher voltage to get that same amount of current because there's just as you said, Neil, a kinetic limitation to get that same amount of current to occur. So that's another way of thinking about the system if it's a two electrode system.
Yeah.
Uh,
Cathodes 304 stainless.
So he's saying new system, mild steel to stainless.
So he's using
new carbon bar.
Using 304 as the cathode, it looks like. Anyway, I mean, yeah, I guess maybe that's just kind of all we can say about it. I'm not sure there's a lot more without
just trying to understand why. Yeah, why is the resistance higher, or why does it require more voltage to get the same current when the other thing, the sacrificial thing is
and I think the other
changed.
Maybe the other point to make is that if your requirement, let's say, of your experiment, right, is to is like a current, like I have to get, this is the current that I need, to plate a certain amount of gold from my solution, okay, and it's requiring more voltage with this new anode, right, compared to my previous one. If your goal is to understand it, that's perfectly reasonable, of course, and maybe something of related to what we've said, just the difference in the kinetics and the processes between those two materials explains why it happens easier on one than the other, hence why it requires lower voltage than the other. If you are having a problem, for example, with the higher voltage that's required on like carbon compared, because it could be the case that, okay, well, this one, the first case I need this current and it's 1.5 volts. I'm just making up numbers, right? Okay. And that's fine. And then with the new material, to get the same current, I need 2 volts. But whatever, I don't care. I don't care what the voltage is. It's just curious to me why it gets higher. Then you can try to explain it just by a difference in processes, something like that. But if you're running into the issue that like, well, because it's requiring 2 volts, I now have other processes that are going to happen, which could be the case because, recognize that the voltage that you get will, that's the potential at each, like that's related to the potential applied at each electrode. And at some point, you could get a voltage that's so high that now you're not just doing, for example, like the electrowinning of gold, but you're doing like some other oxidation or some other reduction reaction that's not desired, right? Like your voltage gets too high and you start doing some other side reaction. So you could run into a problem where like a certain anode that you pick is really a bad idea because the old anodes contaminate the gold. Yeah, so you don't want to use those ones. I understand. But now you might be running into the problem, like I said. Okay, so you don't want to contaminate your gold, so you use this other one. But that one results in the voltage being really high, and if the voltage is really high, I get these side reactions, and that's also not good. So now it's sort of a pick your poison, right? Trying to you have some trial and error as far as what the best anode is to optimize, for instance, minimize the amount of contamination of your gold, and then minimize side reactions if my voltage doesn't get too high. Like maybe you could use like some sort of alloy or some literally two materials as your anode, like a bit of both, kind of. So maybe it like there's a little bit of the sacrificial, piece to keep the voltage down, so your side reactions are low, but there's not so much of it that it contaminates. Like you could try sort of combining materials. You could try something like that. So anyway, hopefully that kind of talks through that for you a little bit, and some combination of those ideas might help you understand and maybe get the best anode for you. So
I also forgot one other thing. One last thing to at least mention about this is if the area of the two electrodes are different, that will also cause voltage changes. And it may be on a scale that you can't actually tell. But if you make it bigger, it usually needs less voltage to drive the same amount of current. If you have a very small area and you're trying to get a lot of current out, you need to apply a higher voltage. So that's another thing to think about.
Yeah, try if you have to regress to your old one, try making it bigger. It would require less voltage. Maybe there's less contamination, something like that. So yeah, that's a good point.
Yeah.
Where are we?
Okay. So Muhammad has a question. He put this both on LinkedIn and on YouTube. Muhammad is asking, what is the most effective procedure for drop casting active materials onto nickel foam electrodes for use in supercapacitors? I have no idea.
So I could talk through this a little bit, Muhammad. There's like a handful of things.
A practical guide, like step-by-step methods.
That I don't know. That's a good question. This is one of these things where, perhaps unfortunately, to a certain extent, there's that's part of the engineering and part of the what I always sort of in a silly way call the arts and crafts part of doing research, right? Like constructing your cell, constructing your electrode. There's often a lot of analysis and of course data and everything on the electrochemistry in literature, right? You don't often find people who are interested or willing, let's say, to publish papers talking about the process itself, because I think people find it more boring or something. But to your point here, it's unfortunate. It's almost like, can't someone just publish like more methods papers? And maybe there are more out there, and I'm not as familiar. I always plug a friend of mine, Yannick Garcini, from the Naval Research Laboratory. He published a really great paper on the drop casting method on glassy carbon that almost everybody uses for rotating disc electrodes. And he gave a tremendous. He's done a tremendous amount of work years and years ago on how to do that. Now, this is not exactly the same as what you're talking about in terms of casting onto a nickel foam, because in that case, it's like a disc. So the geometry is, I would say, easier, a fixed solid disc compared to a nickel foam. So the first thing that I'll say is that part of this will depend on what you're casting, like your catalyst, your material, what it is like physically. And what I mean is, are you coating or casting like nanoparticles or nanomaterials, something like that, right? Or and can it be made into an ink, right? Can you dissolve it in ethanol or water or some other solvent, or is it some nanoparticles don't disperse well into solvents and they make terrible inks, and some make okay inks. So that's the first part of this, right? Because I guess what I would say generally is that if it doesn't disperse well in a solvent to make an ink of some kind, I'm frankly not sure how you could do it other than something like atomic, like ALD, like if you have like an oven and you have like atomic layer deposition and some spray furnace, something of that nature, which is like a more involved and maybe expensive and tricky kind of procedure, right? Most of the time we're using liquid, processes, spraying or painting or coating, right? So that's the first thing. So assuming you do have a material that you can make an ink from, my impression is that the best way to do this, because it's a nickel foam, the other factor to really consider is, do you need the nickel foam 100% coated, or is it okay if there's some nickel still exposed, right? And the reason for that is that if it's not okay for nickel to be there, you're also going to struggle. So this is the other part that's tricky. If you have to have it fully coated, right? Like 100%, like no nickel foam is available. Like it's fully coated, right? Fully coated. That's going to be hard because the nickel foam is so like, it's a mesh. It's everywhere, right? There's so much surface area. There's so many nooks and crannies and tiny spaces that it's going to be tough, right? So what I would suggest, if it's possible, this might be really difficult, but it's like you could think about dipping it, right? If the foam is, if the geometry of the foam works somehow, and you can get like a beaker or a tube, whatever, of like an ink that's very like viscous, and coats well, you could imagine like dipping the nickel foam into like black paint, and then you pull it up, and then it's black paint you painted it by dipping it, but instead of paint, it's your catalyst. So that would be one way to think about like getting it coated. And then usually there'd be other, you would maybe dry it, cook it in an oven at whatever temperature for some time, mass it to see how much of your material's there. You'll need a binder, things like that. And then the last thing I'll say is that the other method that is somewhat accessible, it probably won't coat everything. Like if it's okay for there to be some exposed nickel, is a spray method. So like they make, I actually used this in graduate school, and I was in a lab like some time ago, and I saw someone using the same thing, and I was like, oh, that's cool. I used that when I was in grad school. They make, you hook it up to like a compressed air, and it's like, it's a small little metal spray gun thing with like a reservoir that you put a little bit of the ink in, and it's just, it's like a spray paint, but it uses compressed air, and it sort of vaporizes your liquid stuff. And so you could just basically put your nickel foam up in like a fume hood and like tape it or somehow affix it with a backdrop that you won't care if it gets messy, and you just sort of like spray over it, literally. And you might flip the nickel upside down, spray the back, flip it sideways, spray it. So you try to get as much of the surface sprayed as you can, but that will help like mix as much as possible, all the different parts of the nickel foam. You'll get some of your catalyst on it. And then you'll have to, again, dry it maybe and mass it and see how much you got. But again, the difficult, so you did say it's an ink. Okay. Yeah. Thanks for following up. But again, just the issue is as well going to be how much of the nickel you need. And that, that's somewhat up to you. For sure, there's going to be some situations where having underlying nickel is no big deal because it's mostly inert for your particular electrochemistry. Like it's not contributing. So it's fine. Like it just provides background current. But you might have a situation where the nickel would add catalysis to the experiment you're running, and that's bad. Like you don't want to have the nickel. So you need to like really cover it so you don't get any of that background signal. So whichever of those methods that I talked about might really depend on your needs in your experiment. So hopefully that kind of answers some of those questions for you. Of course, there's a lot of different binders and solvents and different inks that are possible and everything. But the fact that you said you can make an ink, so one of those methods maybe hopefully will allow you to get a decent coating on your foam, and then you can do some electrochemistry.
All right. Very good. Kind of going in order of questions that we're receiving. Andrew V4397 asks, can you go over limitations and best practice when using quasi-reference electrodes? I do molten salt electrowinning work at temperatures where reference electrodes are essentially non-existent. So that's a very good question. While I'd say we haven't worked in molten chemistry or electrowinning, the general idea behind a quasi-reference electrode, or basically all reference electrodes, let me just share my screen. There we go. So with all reference electrodes, I'll use the lasso tool. All reference electrodes basically require a couple things. One is their potentials based on a redox reaction. So you need a redox reaction that governs the potential. You know what? We have a typing tool, so
you should just stay with it like I did, stubbornly, and just keep using.
Oh, we're gonna have a one. Wait, why is this not? Here we go.
I never think to use it still. After all these years, I still never think to use it. You'd think I would.
So we have a reaction that governs the potential. That's the reference electrode potential. This system needs to be it needs to have fast electron transfer kinetic. And then I mean that's, and ideally it doesn't interfere. It doesn't interfere with, and I can't spell, so interfere with chemistry. So whatever you're looking for. These are kind of some of the things that are required for any reference electrode at all, right? Boom. This big list, kind of. And so if we take the Nernst equation, just put it back here. The potential of your reference electrode is it's this guy. It's this guy right here. So you can add any redox couple. This is based on some kind of reaction of a reduced and oxidized species. But usually you peg the potential by just keeping one of these guys constant, or you keep this ratio constant. And as long as this ratio is constant, your potential will be the same. Now, often it's the case that there's no compartments, or practically speaking, you can't put this into like a fritted tube or anything like that. That's what we usually have. Oh yeah, I forgot to mention this thing is supposed to be ideal non-polarizable. That's the other part I forgot to mention here. Ideal non-polarizable. But typically this is what a normal reference electrode looks like. And you add your species in it, and your species has these properties that enables you to keep a constant potential. Now, in a quasi-reference electrode situation, what people often do is you'll just put a wire as a QRE. QRE. It's just a wire. It's a wire that can maintain the conditions of your molten salt electrochemistry. And then you just add a redox species. So O plus an electron goes to R. You add it so that this reaction's occurring here. And when you're doing cyclic voltammetry, decision current, you'll get a CV, like maybe the CV is over here. And this CV corresponds to this reaction. But then, you're looking at stuff that's happening. Maybe you're looking at some catalysis, you're looking at some stuff, and you care about this. If this peak shifts around, right? If you do an experiment like 1 hour later, and this peak is shifting around, then you then note, well, this peak necessarily also shifted around, right? It shifted around by the same amount. So by having this internal standard for your quasi-reference electrode, you're able to tell whether or not your voltage is shifting, and you're always going to report, potential versus, your OER or your oxygen electron. It's just based on this reaction here. So that is and so as it shifts and it moves, it's okay. You're always going to be looking at the redox potential of this guy as it's shifting. And as this guy shifts, everything else is also shifting by the same amount. So you can always correct your voltammogram post-processing from any experiment that you're doing. So hopefully that answers your question. That's really the best practice. Kind of keep it simple. Hopefully it's a system that you understand in your, at a constant temperature, things like that. But that's the practice with using quasi-reference electrodes. I don't any follow up from that, so that's good. Okay.
Oh, sorry, I was muted. I'm an idiot.
Oh,
just
no,
a nice comment from Cool Shows here. Thank you, guys, and your team for the Q&A. I've been emailing your team so much about my research. Well, we appreciate it.
Yeah.
That's what we're here for, my friend. This is a little. I mean, it's almost like we kind of covered this to a certain extent.
Yeah.
Vajihesalehi says, is the voltage stable in the working electrode in the CV2 electrode system? I would encourage you to, if you
rewind
YouTube,
just a little bit.
Yeah, take your slider for time and back up 30 minutes,
maybe half an hour or something, or a little longer than that.
And if you're watching this after the fact, there's timestamps. Alex, we just talked about this obviously a little bit ago. Two electrode systems, and the fact that actually to a large degree, no, it's not tremendously stable, or it's at the very least unknown. So that's kind of one of the fundamental things about two electrode systems. So we won't rehash that in the interest of getting through all these questions. And I think this next one from this person,
who also became a tier 1 member. So thanks for joining us as becoming a tier 1 YouTube member.
Aishanzelf. So I'm not sure if that's meant to be pronounced as these things tend to be here. In any case, this person says, what added info does DQDV give beyond CV if peaks look similar? DQDV.
I don't know what that is.
What the change in charge with voltage?
Change in charge with voltage. So you can, let's see.
If beyond CV, if peaks look similar. I'm trying to think. That's a good question. Where does DQDV show up?
It doesn't show up anywhere. That's the problem. That's one reason why this is a little bit challenging, at least for me thinking about it. Without time,
DQDV.
How does the amount of charge change as a function of potential? It does change because so if you're doing CV,
DQDV.
I'm trying to think if you can get a. So if you there's nothing. I'm trying to think if you looked at the charge as a function of voltage, which means you would have it's not actually even a chronopotentiometry experiment.
It's differential capacity is the term.
Differential capacity.
Yeah, that's the.
Yeah, okay, that makes sense. That's what that is. Differential capacity. Oh, so this is kind of like if you have Q, yeah, it's like the the voltage of a capacitor, or the charge and the capacitor is equal to the capacitance times the voltage.
Mm.
If you took the derivative dq dv, yes, you're looking at the differential capacitance. So that information, in a way, kind of describes some electrical double layers, because it can be the case that at different potentials, the amount of charge you can store in a capacitor can change. It's not it's not
This,
it's tough.
I think this is this one's throwing me a little because it's not part of that I'm aware of. Like, it's not part of like the Nernst equation. You know what I mean? It's not maybe a standard sort of, I don't know, electrochemical equation variable per se, or maybe there's some that I'm not aware of, I guess. But I've seen this in a lot of papers. People do differential capacity. They put dq/dv plots, in addition to CVs, for instance, and they're looking at the, change. I think it's like it's can in a similar way, maybe, and maybe I'm misspeaking a little bit, but my hunch tells me something like DPV, for example, that like really clarifies a peak. For example, a dq/dv plot is going to show you where the charge really changes by potential, and so it's sort of highlighting where an event is taking place, so something of that nature, like where you're charging up,
Yeah.
like at what potential. Now, of course, there's no time axis, so you want to compare CVs that are all at the same scan rate, for instance, because then at that voltage, when that the change in charge is happening at 200 millivolts or whatever, like there's a peak, there's a strong whatever differential capacity at this particular potential. Well, it's time based if it's during CV, so there's a scan rate element here that that's being implied as well. I think I would have to read some more literature about dq/dv, and like I said, I've seen it in a lot of papers. I'm just sort of glancing through a couple of papers now, and I see these plots. Like, it's definitely a thing. People definitely plot dq/dv and have some discussion about it. I think in batteries and supercapacitors in particular, you'll have that kind of thing. For instance, with PIT or GIT experiments, one of the two, if I'm remembering, I think it's GIT. You can get diffusion information from dq/dv. It's part of the calculation of diffusion coefficients. The change, the differential capacities, the slope basically of the capacity versus voltage plot. Beyond CV, I think the tricky part is when you're talking about it in terms of CV, it's more like liquid phase 3 electrode typical kind of stuff. Because with a battery, the main charge discharge curves that you look at that have that big long, plateau, that's Q and V. Like, right, that's voltage versus capacity basically. So like those variables are present, but in a CV, it's voltage and current. Like, it's not charge. Like, charge isn't one of the variables on the plot. So it's a little bit of a different analysis. I guess I don't have enough experience with dq/dv or charge voltage analysis in the context of CVs, like outside of batteries per se. So I guess
I'm trying to think about this because I'm even just thinking like, okay, if dq/dv is 1 versus dq/dv equals 2, what does that mean? Oh, it means that as the rate of voltage changes, which as you mentioned can be like a scan rate, because it's like,
Right.
what is the, does the scan rate change, especially when comparing it to cyclic voltammetry? That in a way means like, oh well, the current goes like this it changes the slope. And it almost makes me think about in a capacitor, it's almost like saying, how does the capacitance change as a function of voltage? And normally we think that, oh, a capacitor just has a single capacitance value. But in some situations, the capacitance will change at different voltages. Even in some electrochemical systems, the electrical double layer capacitance will change as the voltage changes. So maybe
I mean, that's.
dq/dV tells you some of that information.
I mean, I think it has to, right? Because a farad is a coulomb per volt. So
Yeah.
dq/dV is definitionally in units of farads, right? So
Yeah, that's right.
So you are getting. It's almost like the slope. You're getting. So what does it tell you? Maybe the answer to your question, in some very direct sense, is what added info does dq/dV give? It gives you capacitance. Like that's like dq/dV is literally farads. Now, what that means in the context of your CV, at what scan rate, at what, like, there's a lot of follow up questions, but the info that it's giving you, literally dimensionally, is farads, which is capacitance. So it's certainly, at the very least, like you just said, Alex, like it's related to capacitance somehow.
Did we just have a very weird, convoluted way of just saying, oh, dq/dV just tells you about capacitance? It just gives you a capacitance value.
That's right.
And CV also gives you a capacitance value in some cases.
We talked our way over a mountain to get to the other side. We could have just walked around it.
We're on the exact same
we
side.
walked all the way up, all the way back down, and we did a lot of heavy lifting just to get to capacitance. Next question.
It's capacitance.
Yeah.
Like, at least like dq/dt is current, it's but so it's like amps, and it's like, well, amps, but amps is a current, and over time is current, so that means dq/dt must be current, which is amps. Which is, I think, so what you're getting is an amperage from that data.
I just want to note really quickly, it's very important that this is what we're doing right now. Okay, you bear with me. I'll get there.
Okay.
I promise. Hang on. The payoff will be worth
right.
it. The payoff will be
all
worth
good.
it. That's right.
Okay.
We're talking about dq/dV, and this is like current and capacity and charge and stuff, and what is it, and all the things, and it's like, there's so much there's so much question marks.
Patience killing me.
Hang on, this is gonna be great, I promise. Okay, yeah, this is what we're doing. This is what we just did. I want you to be aware. There you go. That's what we just did. We just solved
capacity.
it.
We just solved it.
Capacitance, I guess it should be. Capacitance. Whoops. we just solved the mystery of Pepe Silvia.
Yeah, that's right.
We're just like, it's gonna be all these things, and we figured it out, So anyway, that's it. That's what we just did.
That's what we just did.
We talked circles around, but that's what we do sometimes, because even though we're trained electrochemists, there's so many like little things that we haven't.
Oh yeah.
I haven't like done myself, like as far as in my research days are concerned. So
yes.
Anyway, I hope that kind of maybe helped. At the very least, I hope it was entertaining.
Yeah. At least hopefully it was entertaining.
Yeah. Okay. Well, let's move on then, in the interest of sanity.
Yeah. So,
Karen
Lee 2921 just said, I recently finished your EIS series, and it has been so helpful with fitting my data. My question is about labeling the different components in an equivalent circuit. Sorry for the long introduction. Coming in a symmetric cell, reference electrode, polymer electrolyte, reference electrode. That's the system. The high frequency semicircle is often labeled R bulk of the electrolyte. But in a half cell working electrode, polymer electrolyte, reference electrode, our bulk is labeled as the left side x-intercept of the high-frequency semicircle, and the semicircle is labeled RSEI. This is what I've seen in the literature when people label their equivalent circuit. Wouldn't our bulk in a half cell also be the high-frequency semicircle since we're using the same electrolyte? All right,
So can you tell me,
gotta think about this.
are you getting two semicircles in both cases, or are you only getting one of them in one case? So, for example, in the symmetrical cell,
Mm-hmm.
it's a high frequency semicircle. You're getting a high frequency semicircle, even in the symmetrical cell. And then in the half cell, when you have your actual electrode, your working electrode,
Yeah.
High frequency semicircle in the semicircle. So do you have two semicircles in one and one semicircle in the other? That's my question? Because it sounds like you're saying you get. Let me again draw it, but not with the Pepe Sylvia thing. I'll draw it for real. So, and let me know if Karen Lee answers the question. If there's one semicircle,
just to get some clarification.
What I'm gathering from your question is that the symmetric cell looks something like you have a high frequency semicircle.
All right, Karen Lee got back to us. Yes, I get two semicircles in both symmetric and half cell setups. So it sounds like
two in both.
There are two in both.
Okay,
so I now I understand why the labeling can be confusing, because it's like, okay, you have symmetric and non-symmetric. Okay.
So you have two semicircles. Maybe you have a tail, maybe you don't, I guess. Whether it's symmetrical or, let's just say, working electrode, right? And I don't know. They probably look slightly different. Now, here's my other question, and I'm guessing this is true. Is the first semicircle about the same size for both of them? Maybe this one's smaller or something like that is my guess. So like symmetrical cells, the black curve. I drew the semicircle ridiculous. It's like way too. I don't even know why I drew it like that. But
all good.
So I'm guessing it's something like that, where you have the same semicircle, size wise, roughly speaking, and then maybe another small semicircle, and then I guess maybe a diffusional tail, maybe not, but you have the same one. Okay, so I'll again talk through a little bit, but I'll wait for a response. The circuit that you would fit for this would be a leading resistor, and then it would be more of a CPE, but let's just draw a capacitor for drawing simplification. You basically have two RC units. You might have a Warburg in there too. Again, just for simplicity, just talking about two semicircles, something like this, right? Again, I'm kind of ignoring the Warburg stuff just for the sake of argument here. So let me kind of pull back up the question a little. Let me know if there's a follow-up about any of that here. Let's see. So okay, the R bulk is labeled as the left side x-intercept of the high frequency semicircle is SEI. Okay, so one thing to be clear is that I can't say for certain with your symmetrical cell or really anything else, because I don't know what materials you're working with. You weren't specific. The SEI is only there if you have a material that makes an SEI. So one of the things that you showed is that the symmetrical cell in the literature, they're not labeling anything as the RSEI. With the working electrode, they are. So my assumption is that, for instance, your symmetrical cell would be like lithium or something. And then the working electrode, you have like graphite lithium, something like that. And so you're talking about the SEI because on graphite, SEI forms. Okay. But the reason I asked is if these two semicircles on both, if they're the same size, if that's the case, that's an indication to you that it can't be labeled as one thing in one and a different in the other. Like if no matter what, you're getting a semicircle, like a small semicircle at high frequency in both the symmetric cell and with your working electrode, then that is, it's just, proof is a very strong word, but it's at least very strong evidence that that is something constant to your system and not, it shouldn't be differently labeled. Very often a high frequency small semicircle is related to like a substrate film interface or some sort of interface that's like physical. It's not the charge discharge process. It might be the double layer capacitance up here, CDL, and it might be I don't know if bulk resistance is the right word, or there's some, whatever the resistance is, but it would be something that's common between both systems. Is there a follow up yet or no? Not yet.
No, there's no follow up. Yeah, there is no follow up. I think,
Okay.
because part of the question is thinking about, it's the labeling of our bulk, right?
Right.
And we know that we've always called all our bulk just like the real impedance. That is the x-axis. Sorry, the y-intercept on the x-axis.
Yeah.
And in these two situations, they're calling them different things, right? When you have
Right.
the working electrode, polymer, electrolyte, reference electrode, the symmetric versus the non-symmetric cell, our bulk is labeled as just two different things. And so I would just say I think it is very strange to label our bulk as a semicircle.
So
Like, I don't. Are there situations where that would be the case?
not really. The thing that is throwing me a little is just the word bulk. I assume, for instance, and perhaps you assume as well, if we're reading literature, that our bulk is just another name for our ohm. Oh my gosh, that's way too big of an R. I should have gained better control. Like R0, R ohm, the leading resistor, this right here. This is the
Yeah.
uncompensated resistance or whatever. That is just definitionally the high frequency intercept right here, like between 0 and where it whatever. That won't be this distance. Like there isn't really a
We did.
situation where the width of a semicircle is going to be equivalent to the ohmic resistance.
So Karen Lee, or we just got a follow up. She just
Okay.
said she just checked. I'm assuming it's a she because it's Karen Lee.
Mhm.
Just checked my data. Yes, the first semicircles are of similar size, but not exactly. I
Sure.
think it might be due to different thicknesses of my polymer films.
That makes
So
sense.
in
That
both
makes sense.
the
Okay. So
okay.
to be clear, the polymer film is a commonality between the symmetrical cell, right, and the working electrode. You have a polymer film on both of them. The film, the substrate and the film have an interface associated with them, right? On a small level, microscopic level or whatever, you have your substrate and you have your polymer film right on top of it. Well, there is going to be a sort of RC associated with that interface. Just that's going to be there no matter what. So regardless of what the charge discharge situation is going on, regardless of what electrolyte you have, regardless of anything, there's going to be that interface, regardless of what potential you're at, whatever. Now, the thickness of your polymer level, whatever, that will change some of these. The resistance might be a little higher because so now here's the thing. This is, again, some of this is semantics. If what's being called R bulk, this is just it's what's tripping me up. Maybe it's tripping you up. Is like, what does bulk mean, right? Well, if what they mean is the resistance, so to speak, across this interface, this substrate polymer film interface, fine, sure. Then that certainly could be this width here, the width of a semicircle, right? But that also can't be this intercept. It can't be both. It just can't. So you just need to use a different word. Like again, R0, whatever would be what you would call this, or R ohmic drop, IR drop, whatever the name is for the standalone resistor, that the leading resistor that's present, in all systems. That's like the electrolyte, the cell cabling, all of that stuff leads into this resistor. But that substrate film, polymer film, whatever interface, if that's what we're calling our bulk, then it should be the same for both. That width of that semicircle is our bulk, is the same one, whether it's the symmetrical cell or the working electrode. That's my impression. So if in one case they're calling it the SEI, I would dispute that personally. That would be my impression. That I would not say that that's the SEI. That if it's the substrate polymer film interface from your symmetrical cell, and then it shows up at about the same size, maybe slightly different because the thickness of your polymer is a little bit different, and then they're calling that SEI, I would say that's incorrect. That's my educated opinion about that. And I think it seems like that's the conclusion that you're drawing as well. And I would say if that's what you're thinking, and I would say you're correct. Because again, this is one of those fun things where it's like a lot of times the system or the applied potential of your impedance will impact the semicircles. It'll impact the entire spectrum. But if there's a part that's not changing, that should tell you something, right? And one of the things that doesn't change much is the high frequency intercept, the R ohm, R0, whatever you want to call it, right? That doesn't change a lot of times. And that's because your IR drop is, let's just say, relatively constant. If your electrolyte concentration and strength is the same, your cell cable leads are the same, whatever, all that stuff is the same. It'll change ever so slightly because science is tricky, but for the most part, it's roughly the same, no matter what your voltage is, no matter whatever. And in your case, you have this extra added component or element, if you will, of the substrate polymer film interface. Like that's constant. It's there no matter what your applied voltage is, no matter whether it's a symmetrical cell or not. You have this polymer substrate interface that's always there. You change your voltage, it's still there. So the fact that little semicircle doesn't change, it changes a little, but not much, should be an indication that you shouldn't label it one thing in one situation and in another and another. Like you've, by doing what you've done with the two different cells, I would suggest you have proven with reasonable certainty that it should be labeled the same in both. That's my impression.
All right. Let us know if you have any further questions or information.
Great question.
I think that's
great.
no, it's a very good question.
Good intuition
and good detail in describing the kind of weird stuff.
We've had really good questions today. I haven't even been mad once.
Oh yeah.
I'm very.
Well, there's still like 20 minutes left for you to get mad. All right.
It's been a good day.
I feel like it's bound to happen now.
We're doing really good today. I'm gonna keep up the positivity.
We are doing well. All right, so this question is from Mono2176. When running cyclic voltammetry CV on a CHI workstation, I notice a sudden current discontinuity at the vertex between segment 2 and segment 3, even though the potential is continuous. Any best practices to avoid this? So I think we would need to know. We need to know a little bit more about the situation. Some of the models, if you're listening and you're hearing this, some things to a couple questions and things I would ask are, you have a few segments, but can you repeat this? Can you cycle back and forth, more than say 3 or 4 times, and actually get this? It's like, it's not just happening in segment 2 and 3. It's always happening at the same repeated potentials, where you're seeing this current discontinuity. Or if you are sweeping maybe 50 times and you're always getting this discontinuity just in segment 2 and 3, That is a weird fluke, but if after that, then when you're sweeping, it's perfectly normal, then it might be something where it's like, oh, the electrochemical system hasn't stabilized or something at those first, few potentials and sweeps. We would need to know a little bit more, I think, about the electrochemical system itself. If you change the potential with which you're sweeping, does that also change the current discontinuity? I think I'd have to see what that looks like in the voltammogram. That usually is what Neil and I use to give us an intuition as to what might be happening. So one thing I have observed, which can be very hard, is you may run into a compliance voltage issue. And so as you're sweeping, you're going to higher and higher potentials. If you have a small counter electrode, for example, it might hit the compliance voltage limit. And maybe what CH does is it just doesn't show you the current at those potentials, and then it kind of jumps when it's sweeping back as part of segment 2 or part of segment 3. So that's another thing to think about. But so if you can provide us with a little bit more information about, of course it's hard to tell us like what the voltammogram looks like, but any additional information about what the discontinuity looks like. But those are my kind of things, like change the potential, like see if changing the potential makes it so that the current is still continuous. Do multiple scans back and forth to see if it's only segments 2 and 3, or if it's actually repeating every, if you have a 3 or however many segments CV, it's constantly repeating the exact same areas. So those are things that I would try, not knowing anything else about your system. I don't know, Neil, if you have any other thoughts or ideas.
The only thing that I had thought about, which was, I don't even know if it's exactly what's going on, but I'm thrown a little by the idea of a sudden current discontinuity at the vertex between two segments. Like the vertex between two segments is when the voltage is probably, or the potential's changing directions. Yeah. So I guess what I mean is like,
maybe what's being shown is normal.
Well, yeah, either that or it's just near the vertex. So like, this is the kind of point that I'm trying to imagine in my mind, like what we're seeing. So it's like, let's say we have in a perfect world, is our CV like segment 1, that's segment 1. And then segment 2 is like down this way, right? This is segment 2. So you're saying there's a current discontinuity, right? So this is current and this is potential. So we're saying there's a current discontinuity between segments 2 and 3. So if like segment 3 is coming back, it's like, if you're saying a normal CV just looks like this, like it, right? Like this is segment 3. It's like we went this way and then we went this way. So I'm wondering if the question is like, why does the current just go up when you go back? You know what I mean? Like is that, I doubt that's the question. Or is it like, it goes like this, and then there was like, you saw something like that, like the current.
It's just a gap. That's a good
sometimes question. That's just sometimes the answer is as simple as like, it's just a potentiostat thing. Like it's just the way it's plotting how quickly it can gather data. Like it just doesn't connect the line. No, there's nothing wrong. Or is it really like, segment 1, 2, and it was just somewhere near, you had something like that. Like, you know what I mean? Like
that's right.
I don't know which of these scenarios is going on, is kind of my point, because if it's something like you're seeing some weird feature, everything you said is good. Like go multiple times as it keeps showing up, sweep more, change your voltage limits, see if you observe it or you don't. It could be a current range. It could be a potentiostat thing, like a current range. Is it a chemistry problem, or is it really just something like this or this, and it's actually a normal phenomenon, and
that's true, and
you don't have any reason to worry, right? Is my point. Like you might be perfectly fine, like don't worry about it. That's actually just a normal feature of cyclic voltammetry. So I think that's the difficulty. So apologies if we can't really give you more insight, because we can't see the voltammogram
we don't know what it looks
through
like.
YouTube comments. But
Yeah.
hopefully some of those ideas you can kind of think through and then troubleshoot for yourself. But maybe if anything, if what I described, those first two cases, like if it's just changing directions, then nothing is wrong. Actually, that what you're calling a discontinuity is actually just like normal behavior, so to speak. So maybe it'll put your mind at ease. But otherwise, I guess we have to maybe see the data to be able to really more clearly comment on it, because exactly what you mean by discontinuity, like what it really looks like, it'd be easier to pass judgment on it if we saw it, obviously.
Yeah, if we saw it, that's true. That's a good point.
Hopefully that's a little bit helpful for you though, Mono. So
yes. So there's a couple questions. I think Andrew was mentioning something earlier where it's like,
I think that was the DQ/DV craziness, something about whatever.
Yeah.
So something like that.
Okay.
But
so that was that.
All
right. We don't need to go. Yeah. We don't need
Charlie
to go there.
conspiracy theory land. That was fun. But
Yeah.
just working our way around all over. So
yeah. So the next question from AVG Edits. Hello, I am recently starting with electrocatalysis for alkaline HER. How can I analyze LSV curves to study the HER activity of the electrocatalyst material? Very good question. Good way, starting your research off. Typically, what people do, they won't simply use LSV. They'll actually use RDE or like a rotating disc electrode when studying catalysts. So in general, you'll have some kind of electrode. It's some kind of glassy carbon, so this is all black. This is make this thicker. So you have some kind of you have some kind of electrode, some kind of carbon electrode. You put your let's see something a little brighter. You put your that doesn't do anything. Let's put it here. You put your catalyst. You would drop cast your catalyst onto this electrode, and then you would put it into your alkaline cell. And then you'd probably you'd stick this in, and then you'd put a counter electrode, maybe it's some kind of platinum wire, and then you'd have maybe a mercury, kind of a mercury oxide reference electrode for alkaline systems. So this would be your physical setup, right? This is the physical setup. Now, typically, from an experimental perspective, once you have this physical setup, you'd want to perform ideally something. Neil and I usually encourage rotating disc electrodes because it tends to be a little bit more accurate when it comes to studying your catalyst. But if you're doing a reduction reaction, you would sweep or do RDE, sweeping negatively, and ideally you would see this decrease in current or an increase in the cathodic current associated with the reduction, right? So this is like HER. All right, and you would push this, you'd keep pushing this down, and then maybe it sweeps back or something like that. But you get this HER, and if your catalyst is really good, maybe you would get a higher onset, a lower overpotential, with your catalyst, something like that. Those are some of the very basic types of experiments that you would do. Very, very simple. The next thing that is typically done is you would take this data and you would do TAFL analysis. Of course, this is why we recommend actually doing RDE, so using a rotating disc electrode. Because when you just do LSV and you get these kinds of plots, when you move to taking this data and then plotting something like the overpotential, eta, versus log of the current, you end up getting these Tafel slopes, and I don't know if I'm doing this in the right direction, but you end up getting these kind of weird Tafel slopes. And the Tafel slopes help you gather some information about the number of electrons transferred, what the overpotential is. But sometimes these are, the accuracy of the Tafel plot is heavily dependent on the accuracy of your current data. And the current data in a typical LSV experiment, even at low scan rates, isn't it's convoluted with mass transport problems as well as capacitance problems. So the current that you have is not really reflective of the pure kinetics of your catalyst. When you use a rotating disc electrode, it's best to do almost like a chronoamperometry experiment where you're literally doing RDE at potentials, or you actually do this at very slow scan rates, and the data ends up being much more accurate. This would probably be, it might be a little bit lower or something like that, but RDE ends up giving you higher quality data. But I just gave you like the very like big bird's eye view picture of, I'm doing HER in alkaline systems. This is my setup. How do I analyze my catalyst? It's like, well, this is what you do. In a nutshell. That's kind of the quick answer, if you will, for like, how can I analyze my LSV curves and stuff? Well, we recommend doing things like RDE and Tafel analysis to get you kinetic information about your electrocatalyst.
You're getting very close to making me angry talking about Tafel analysis.
I know, but I saved it. I told them, I showed them the way. The RDE is the way. Just doing LSV is not sufficient. Preaching, to the choir, just spreading the gospel of how good the rotating disc electrode is.
It's true.
So
it's true.
AVG edits, it's important, because there are so many Tafel plots that are out there. And
I made a meme about it. Put the meme up.
Oh yeah, that's right. Hold on.
I made a meme about it.
I also get into the slouch position.
Yeah, you gotta get
concentrate
clown. It's the clown. No, is it the clown one?
There we go. Let's see.
Oh, there we go. Yeah.
There we go. Okay.
That's right. Yeah, you can. I had a good time with this one.
Okay.
Well, I'm not mad because I think it's funny, so we're good.
Yes.
It's fine. I spent a whole live stream not getting mad. This is good. Okay. All right, let's try to get to the last couple questions here. We got about 5 to 6, 7 minutes left or so. Let's see. Anwar Saeed Khan says, I have prepared a composite of polypyrrole with different mass ratios with metal oxides. Upon electrochemical testing, the CV increased, but the charge and discharge time decreased for low mass ratio. First of all, there's no question. I guess, I'm assuming you're just kind of wanting to know why is this occurring. I also don't know when CV increased. I guess I'm assuming what you mean is you're doing like supercapacitor kinds of tests would be my guess here. And so if you're doing like CVs, I'm guessing what you mean is the current increase, which the current is equal to the scan rate times the capacitance. So it's proportionate. So anyway, an increase in the current of your CV. So just to be clear, what I'm guessing is that you have like CV1, you have some window like this, and then like CV2, you're saying it increased. So I'm guessing you mean like the current response increased. So you had something like this. I'm guessing that's what you mean, because the current that you get basically this current here, is equal to the capacitance times the scan rate. Anyway, I'm assuming that that's what I'm assuming you mean. And the other part of this was that the charge and discharge time decreased. I'm trying to think that through. Like the time is related to like you think about the time constant, that's like capacitance times resistance, I guess. So if the capacitance went up, the time should also go up, but you're saying the time went down, which suggests that the resistance went down. I'm just thinking out loud here. I'm not sure if you have any other thoughts about this or not, but
No.
I guess, yeah, I guess maybe I'm also inferring like multiple questions from a statement. So I might need to not go down a crazy rabbit hole here, but
yeah, I'll be honest. I learned something very interesting on my most recent trip to Boston. I was talking to a scientist who had worked with polypyrrole, and it was telling me that pyrrole contains nitrogen inside of it, and you can substitute the nitrogen for arsenic. They're in the same column. Do you want to know what the pyrrole version of arsenic is called?
No, I don't know.
Arsehole.
No, it's not.
It is.
Oh, that's not. Oh, that's perfect.
It's perfect. Yeah, when you replace the arsenic, the nitrogen arsenic, you call it arsehole.
It's called
like that's pyro, what it's called.
Arsenical, arsehole.
It's called arsehole.
That's a scientific chemical name.
That is a scientific chemical name of
that's phenomenal.
Of when you replace the nitrogens in pyrrole with arsenic, because they're the same.
It's a group 14 element, right?
It's a group 14 element. It fits.
That's ridiculous.
Anyway,
sometimes chemistry is just perfect. That's phenomenal. So that's all you're thinking about with this question.
All I'm thinking about. I'm just like, I'll just like charge there, and increase mass rate. I'm not really so sure, but
I'm just
he
mentioned
polypyrrole, and I'm like, I now know what the name is when you replace the nitrogens with arsenic.
That's phenomenal. That's terrific. Can you imagine having to like deliver your PhD thesis and say that over and over again with a straight face?
Oh, I think somebody had a great time doing that.
I don't think I'm mature enough to do. I would have to change PhD topics. I just wouldn't be able to do it. I would just call it pyrrole. I don't care. I'm calling it pyrole.
I'm calling it pyrole.
Well, anyway, back to the point at hand.
Yes.
I might just leave this one here because I guess I don't totally know what the question is. And there's a bit of ambiguity here. Like I said, before I talk myself into another 30-minute spiral and make up a bunch of things. I think I showed you what I assume is you're talking about, but I guess I don't totally know. And I'm not even sure precisely what your question is. So maybe we'll sort of pass on this one for now and move to, I guess Vignesh has a couple of questions. We'll try to get to this as the last questions here.
Yeah.
So I guess, again, another thing with the two-electrode here, Vignesh, is whether potential with respect to RHE and potential in two-electrode is the same. No, it's not.
Unless your other electrode is in RHE.
In RHE, yeah, yes. Exactly. But no, and again, much earlier in the live stream, maybe 1 hour ago at this point, we talked a lot about
over an hour ago.
Yeah, we talked a lot about two-electrode systems and CV and the peaks and a lot of these things, and Alex drew some diagrams and everything. So I would encourage you to go back or click on the timestamp, which will appear later. At the moment I'm saying this, it's live. It's not there. It will be soon. But we talked about two-electrode systems, and there's a deep uncertainty associated with what the potential is at any moment in time. You don't have a reference, so you don't know if it's versus anything, versus RHE, versus SCE, versus anything. You just don't know. So no, they're not the same thing unless by happenstance, or you have an RHE physically in your as your electrode.
Yeah. And his last comment is like the total charge given by Pine instrument is different from charge calculated manually by current times time. It's because of integrating the area. So we would need to we need to see it, like how you're using the tool and how you're calculating it.
Yeah.
There are We also need to figure out what version of the software you're using would also tell us, so we can
Yeah.
actually look at
And yeah, there's a
how
lot of
it's
open
calculated.
questions here. The charge is calculated by integrating. If you're just taking a current and multiplying by a time, if the current is constant over that entire time, you will get a roughly accurate charge, because it's a rectangle. But
Yeah,
yes,
it's a
it is an integration. And then, like which version of the software you're using would be helpful, as well as, if you're using the area tool, for example, in Aftermath in our software, you got to know where the baseline is. Like, it allows you to move the baseline and calculate the area like a bunch of ways. It's quite comprehensive. But in your case, that might be hurting you if you're sort of wanting it, a straight baseline with respect to zero or somewhere. And it might be, it'll calculate the area under anywhere. And also, if you have it crossing the trace itself, it might be calculating multiple areas from different places. So there's just some open questions here, but please, reach out to us if you want, or one of our reps, if whichever region you happen to be in, and we can definitely look into this for you. But we might need to see some data and check all of the specifics, to see what value you're getting, and see if it's just a minor adjustment that you need to do with the tool, for instance, or if maybe you could update your software, and it'll work a little better for you, something like that. But please reach out to us. We can put our email address, I think, in here.
Yeah, I'm gonna put.
Okay, you're gonna put it. Yeah.
Yeah.
So we'll put our email. You can email us directly, or again, if you're in a different country, you might have one of our representatives you can reach out to, and they can likely also help you too. So
Yeah. Email the PineWire at pineresearch.com email
Yes.
address I put in the chat, and that will and just say like, oh, I spoke to you on the live stream about stuff, and then we can get the necessary information from you about it.
Yes. All
Okay.
right. Well, I think
that's it.
that is gonna do it. We are not in next week, and then we will be back on the 19th, I think.
Yes. And then we
And
won't
then
be back again for a long time.
for a while, probably,
For a
'cause we have
while.
the holidays and stuff, so it'll get a little bit dicey. I hope everybody else will enjoy some holiday time, unless you're in grad school, in which case you don't ever get time off, and that's how it goes.
Yeah. That's right.
But no, I do hope everybody has some time this season to enjoy not working. So, but until then, I hope everybody has a good rest of your weekend, and we won't see you next week. We'll see you in a couple weeks. Thank you, everybody. As always, we appreciate the the engagement and everything. So we'll see everybody in a couple weeks, and take care.
Take care.
Bye bye.